All right, today we're going to start section 3.1, and we're looking at something called Numeration Systems. 3.1 is going to feel quite a bit different than the rest of the chapter. 3.1 is a historical background. That's what it is. If you've taken contemporary math, like I know Savannah took contemporary math with me, we talk about some of this in contemporary math. So you may have seen some of this before, and you may not. My biggest goal and hope from this section of material is that it gives you an appreciation for the number system that you're working with and how it is an improvement over things that were tried beforehand, okay? So we're going to take a look at some different numeration systems, but the one that we actually use that you should know its name for is the Hindu-Arabic numeration system. That's the one we use. It was developed by the Hindus, and it was transported to Europe by the Arabic. In our number system, all of our numerals are constructed from 10 digits. What are our 10 digits? 1, 2, what else? Okay, so 10 is actually not a numeral because it's got 2 of them there, and we'll go backwards. As Ty mentioned, we have the number 0. So our 10 numerals are actually from 0 to 9. Does that make sense to everyone? Okay, those are our 10 numerals. Another feature of our system that you've probably taken for granted, and you will not after this chapter, is that we have a place value system that's based on powers of 10. So we have like the ones place, the tens place, the hundreds place, but 100 is 10 squared, right? Everything's number has a different value depending on the location of it. Right, like one of my daughters last night kept writing this down, but she meant to write down this. Those are very different numbers, right? The location of those individual digits matters because it's the place value system that we have. The other thing that I'd like for you to remember is this exponent notation. So when we have a to a power of n, it means that a is multiplied together n times. And we're going to see that come into play. Even already I mentioned that if we have the number 100, it's really 10 squared. So we're going to see powers of 10 or powers of other numbers in our different numeration systems. All right, so our first numeration system, way back, like Moses' time, right? That's a long time ago. I don't care how you count time. That's a long time ago. And that's the Egyptians. The Egyptian numeration system, and let me just tell you as well, these are the symbols or pretty close to it that your book uses. They look a little bit different than the other book that I have used for contemporary math. They look a little different than the last book that I used to teach this material at another university. So there is some variation. That's okay, right? It's kind of like, not this is a perfect comparison, but it's kind of like people who write this 4 versus this 4, right? They're both a 4, but they look a little different. So if you're looking at that and you're like, that doesn't look like what I've seen before when we talked about it, that's okay. It's okay. This is what your book's using. All right, so they have these different numerals. The first one is called a vertical staff, and it looks like a tally mark or like our number 1. And that's actually really nice because it has the value of 1. The next one's called a heel bone. Looks like an intersection symbol from what we did in chapter 2, right? And it has the value of 10. Okay, heel bone's worth 10. The next one's a scroll, and I'll also tell you the scroll is actually also drawn upside down, left and right. That doesn't seem to be an issue with the Egyptians at all, sort of the direction of these things. Your book draws it like this. The scroll has a value of 100. The fourth one is called a lotus flower. I don't draw very well, so I will promise you that I'm not going to be super critical of your drawings. Just do your best. Make sure that we can distinguish, the lotus flower from the heel bone. We should be able to do that, right? So this is a lotus flower. The lotus flower is worth 1,000. To be honest, the one that I draw, the poorest is the pointing finger. So it's supposed to be looking like this, right? Like the finger's going kind of like this. Right? It's pointing at something kind of awkwardly. What do you think the pointing finger is worth? Yep, it's worth 10,000. The next one, your book calls it a pollywog. I've had other books call it a burbo fish. I had one of them a long time ago called a tadpole. But regardless, it should look like a little fish, right? It's even got a smiling face on it. He's very happy. How much is that going to be worth? 100,000. You got it. And the last one is an astonished man. He definitely looks different than the other resource that I teach with in contemporary math. He looks almost like a woman in a dress, actually, the way that they draw him here, which kind of makes sense if you think about Egyptians' clothing, so I can get that. And I think he's really astonished because he's worth $1 million. That's what I think, right? He's very, very excited. I mean, I would be excited if I were worth $1 million, wouldn't you? Of course you would. Yeah, he's excited because he's worth $1 million. We're going to go with that. Now, we're going to be looking first, not at how we turn our numbers into theirs or theirs into ours, but we're going to sort of put our hats on, and for a moment, we're going to pretend like we're an Egyptian. Okay, think about the song if you wish. Okay, you're going to pretend like you're an Egyptian, and you're going to be answering these questions within their system. The goal is not to turn this number into our number, find the answer, and then turn it back. That's not the goal of these problems. It's to think for a moment like what you would do if you were there. So this symbol has three scrolls, and then a heel bone. So for a moment, I want us to recognize that they always put the biggest value in front. So notice the scrolls are coming before the heel bones, right? Scrolls are worth how much? 100, and heel bones are worth 10. So the hundreds are coming before the tens. And I would like you to think about what you would do to get the number that comes before this. Well, you can't end with 10, right? That's the last digit. You need to be ending with what? With no one less than that, 9, right? So all the scrolls at the beginning stay scrolls at the beginning. Those don't change. But the heel bone has to be downgraded, right? How many, or what symbol am I going to write next? A vertical staff. And how many am I going to write? 9 of them. And no, they do not make hash marks to mark off 5s. That's not a thing. This isn't a tally system. There's literally 9 staffs right there. What would we do to find a number that comes after it? Well, right now, again, it ends with 10. So instead of ending with 10, what would it need to end with? A 1. We need to end with 11, right? So we need one more on the end. So we just sort of tack on or add on to the original number one more. That's the number that comes after this. Now what we're going to do is we're going to find out what this number, that is the original number we were given, is in our system. Okay? We've already talked a little bit about what it is because we said that the scrolls are worth, that's not a very good scroll, it looks like a 9. Let's try that again. Oh my goodness. There we go. The scroll is worth 100 and the heel bone is worth 10. So we have 3 scrolls, so that's 3 hundreds. And we have 1 heel bone, that's 10, for a total of what? 310. Okay, nod your head if that's all good. Okay, their system is pretty easy to work in. It's really not too bad. I cannot say that for every system. But theirs is pretty straightforward. Okay? Now we're going to go the other direction. We're going to take one of our numbers and we're going to write it in their system. Okay, so the 2 at the beginning is in the what values place for us? 10,000s. Okay, it's the 10,000s place. So what symbol do they have in the 10,000s place? The pointing finger. So how many pointing fingers am I going to draw? 2. You're going to draw 2 pointing fingers. Mine are terrible. 2 pointing fingers. The 3. What symbol is in that location? That one's my lotus flower. So how many lotus flowers do I need? 3 lotus flowers. Something like that. How about the 1? I'll have 1 what? 1 scroll. The 4. Yeah, 4 tens or 4 heel bones, right? And the 5. 5 staffs. Okay, so pause with me for a moment because you're going to be asked these questions either on your homework or group work eventually anyway. But what do you see if you were thinking like an Egyptian and you were really working with these kinds of numerals all the time as some potential pluses and some potential minuses of this system. What are some pluses? Yep, exactly. Pros and cons. Yeah, what's a pro? What's good about this system or makes it easy to work with?
Easy to see how the numbers break up.
It's really easy to see how the numbers break up, right? Not only do they go from biggest to smallest, but they just repeat digits in there. I think that's the biggest pro for me, is that it's easy to see the numbers and how they're broken apart and what they represent, right? There's no ambiguity. Now, that may not make sense yet because our number system doesn't have ambiguity either. But we're going to encounter some number systems that have got some big issues. So it doesn't really have any ambiguity. What's a con? What's a negative of this system? You might have to write a whole bunch. What? Same thing, yeah. I mean, like, imagine if you were writing down the number 99,999. My word, how tedious would that be, right? That's not cool. Maybe easy to read, but it may be tedious to work in. Okay? So there's some pros and there's some cons here, and we're going to kind of talk about those as we encounter these systems. Ready for system number 2? Okay, moving forward a little bit, we've got the Babylonians. The Babylonians literally have 2 symbols. And I will tell you right now that when I draw them, I'm going to draw them a little bit differently than this just because the shading in ends up taking some extra time. So when I draw this first symbol, mine will kind of look like a hollow upside down triangle kind of thing. And when I draw this second symbol, it's going to just look like a less than sign. So these do have specific values, just like before. The value of the triangle is the value of 1. And the value of the arrowhead looking one, that's what it's like, an arrowhead, is actually a value of 10. Now, immediately you should be saying something like, well, what if the number's really big? Right? You'd be drawing a lot of 10s, wouldn't you? So there's got to be something else going on here if this is all we have to work with. Agreed? Yeah, there is. And in fact, you see that there's a properties listed below. They have a place value system. Okay? So much like we have a place value system, like we only have 10 digits, right? If we were just writing our digits down 0 through 9, the 10 digits, you might ask the same question. Well, how are you going to represent a big value, right? Well, we have a way to take care of that. Our way that we take care of it is that we have place values, and our place values are in powers of 10. We'll talk more about our system later, but we do have that. They have a place value system as well, but their place value system is in powers of 60. Okay? So if you write any number from from 1 up to 59, you're just going to write symbols repeated, just like the Egyptians would have done. So if you wanted to write the number 59, you'd write 5 of the arrows followed by 9 of the triangles, and that would be 59. Okay, everybody with me so far? But if you want to write something bigger than 59, that's not what you would do, right? So if you wanted to write something that was like 109, well, you'd have to use 2 place values to do it. Just like if we wanted to write a number that was bigger than 10, right, bigger than 9 really, we'd need 2 place values to do it. Okay, everybody with me so far? I know we haven't actually done one, but are you tracking with what I'm saying? Okay. All right, so let's see one of their numbers so you can see how funny it looks, first of all. Look at all those repeating symbols. There are a lot of them. Here's what you need to know. Guaranteed, anytime you change, just like with the Egyptians, it was big symbol and then small symbol. Same thing. Anytime it goes from big symbol to small symbol, you can have that within one place value. So this is a larger value. These are smaller values. All of this is cool to be one place value because it goes from big to small. However, the number in front, the triangle in front that's a 1, has to be a different place value system, a place value within your number, because it's smaller than what comes after it. So in some sense, we could say that this number has 2 place values, minimum. That's all we're guaranteed anyway. And it breaks right here. This is one place, and then this is one place. Okay, so far, so good. Yes? Okay. So this place, the one that's underlined on the right-hand side, is the 1s place. And this place would be the 60s place because it's base 60. Just like in our system, we'd have the 1s place and then the 10s place and the 100s place, right? They're going to have the ones place, and then they're going to have the 60s place, and then they're going to have 60 squared, right? 10 squared is 100, 60 cubed, and so forth. Now, before we go converting, we're going to, again, think like a Babylonian, okay? So we've got a bunch of these symbols on the board. The first question says, what number comes before this number? Well, literally what happens when we try to find a number that comes before it is we want to take one away from it, right? Can I just take one off the end of this one? What does it end with? Does it end with ones or does it end with tens? It ends with ones. So can I just take one off the end of it? Absolutely can. Okay, so if I just ending with ones, I just have to take one away. All right, imagine having, like the Legos all sitting out. All I got to do is remove one Lego from the pile. All right, so writing the number that comes before this means writing all the same things that are already here in the same denominations they're already here in, except that we need to remove one of them at the end. So I've got the triangle, followed by 5 arrows, followed by 8 triangles. And mine are kind of overlapping connected. That's just because I'm just cramming them in there. That's silly for me, but they don't need to be crammed again together like that. They can be separated. But there's 8 of them. Okay, so think about what you do when you want something to come one after. Well, you add a 1 to it, right? Okay, this is what we did on our last one over here too, right? We added a stroke at the end, or we took a stroke away. If there's no way to take a stroke away, we had to find a way to change something to take it away. Right? We essentially turned a heel bone into 10 strokes and we took a stroke away. Right? That's what we did. So over here, if I add 1 triangle to the end, how many triangles am I going to have? 10. But we have another numeral to represent the number 10. It looks like a arrowhead. Everybody good so far? Okay, cool. So now we have an arrowhead grouping with the other arrowheads. How many arrowheads does that give me? 6. How much is 6 arrowheads? 60. But this value system has a place value system of 60. So we're going to trade our 6 arrowheads in for what comes next. Well, whatever comes next is the stuff that was before with that single 1. So the number that comes after actually looks like this.
How do you know it's not 2?
That is a very good question, Savannah. Did you guys hear her? How do you know that that's not 2? What does it feel like you need? It feels like you need a 0 to hold the place, doesn't it? And do you know what? They don't have one. This is a flaw, right? This is a big problem. Because if you were doing some sort of accounting job and somebody owed you, in this case it's $260, it's $120. We'll just say $120, right? And they paid you $2, that'd be a problem. Agreed? Yeah, that's a problem. So there is a flaw in this right off the bat. We have no way to have a place value of 0 just putting in there. We have no 0 to hold the place. So that's what's going on in C. It says, how else could the value in V be interpreted? And Savannah, you told us, what is it?
2.
It could be interpreted as a number 2. Not only that, but it also could be interpreted as though there was a break between them, because there's nothing that prevents that interpretation. So it could be that this is 160 and this is 1, and this could be the number 61. That's not what we want either, right? It's not supposed to be 61. It's not supposed to be 2. It's not supposed to be 61. It's supposed to be 120, actually. We haven't actually calculated it yet, but that's what it's supposed to be. So it says, what is this value in Hindu-Arabic system? And it means the original value we started with. So we're going to go back to the original value now. The original value we started with, which is on your paper, has a triangle, 5 of these arrows, and then it had 9. And we said that what we're going to agree to do in this class is that the only breaks that we're going to make in place value are going to be those we're forced to make. If it goes from a smaller symbol to a bigger symbol, that forces a break in place value. We're not going to say that there's any other place values unless we're forced to say there's a place value break. So this is one place value. and this is 1. This is the 60s place. This is the ones place. So how many, that is, what is the numeral in the 60s place?
60.
It's a 1 and it's worth 60. So I have the numeral 1, it's worth 60. How much, or what is the numeral value in the ones place? It is 59. There are 59 ones. Okay, so another way you could think about this is think about currency. Money works pretty well. I don't know how much you guys actually use real dollars. I still do. You probably scan a lot of your stuff, but pretend for a moment you used real money. And in this system, all you had were $1 bills and $60 bills. Can you picture that? Right? No, Sarah says no, I cannot picture that. It's imagining something that's weird, right? Yeah, it is. So we're going to pretend we only have two kinds of bills, $1 bills and $60 bills. Okay? So this is saying I have one bill that says 60 on it, right? And I have 59 ones. Right? Well, I can still figure out how much total money I had. I would take 1 times 60 because that's what it's worth. And I would add in the 59. 60 plus 59 would be 119. In Hindu Arabic, this number is 119. And the number afterwards should be the number 120, right? These two triangles here is supposed to be the number 120. But again, there's no way to distinguish that it's not the number 2. Right? Savannah?
So let's say like that was on a quiz or a test or something,
Yep.
and it had those two.
Mhm.
It's like, what's the value of this?
You would say 2.
We
Mhm.
would say 2.
You would.
We wouldn't say 1.
Nope, you wouldn't say 120. It wouldn't have been structured that way to trick you either, so no, yeah. Okay, I think we have one to go the other direction, don't we? Yes. Okay, now we have the number 43,205 in our system, and we're going to write it with triangles and arrows. Okay, so this is our first exposure to how we do this for most of you, at least in this class it is. What we're going to be doing is we're going to be doing, I call it a division algorithm. Algorithm just means the way we do something. Okay, so it's a division process. And I need to know in this division process what my place values are. So we've already established that we have the ones place and the 60s place. The next one I mentioned would be 60 squared, and we would keep going, and it would keep going on forever. Does that make sense? Just like our place values, powers of 10 go on forever. But what I need to know is I need to know what these values each are. So clearly 1 is 1 and 60 is 60, but what is 60 squared? It is. It's 3,600. What is 60 cubed?
About 216,000. Yeah.
Okay. I've gone far enough in terms of writing these out because I just need to make sure that the 43,000 is smaller than the biggest number I've written, and it is. So I don't actually need this one right here because it's bigger than the numbers I've got. Okay, I only need to know the place values that are smaller than the one I have. And here's what we're going to do. We're going to take that 3,600 and we're going to divide our number 43,205 by 3,600. But I'm going to show you a little bit of an imagery that's going to help us out keeping this in order and organized. Okay, so we're going to actually put this in a very real sense under a house or under a box. Okay? And I want your calculator to do the work for what we're doing. I would like for you to divide 43,205, that's our number, right? Yeah, by 3,600. And what I want to know is the whole numbers number of times it goes in. How many? 12. Okay, everybody good? Got a 12? Maybe it says 12. It should say 12 point something, right? Okay, good. And then we're going to actually multiply 12 times 3,600. So what's 12 times 3,600? So we're going backwards and multiplying this.
42,200.
And we subtract. Okay, so that subtraction, please don't grab your calculator. What is 43,205 minus 43,200? Mm-hmm. Okay, the remainder, the 5, is now going under the house. And while it doesn't necessarily make sense what I'm about to do, trust me, we're going to need it later. We're going to simply divide by whatever comes next in the list. We've already divided by 3,600. Now we're going to divide by 60. How many 60s are there in 5? 0. What's 5? 0 times 3 times 60? 0. And what's 5 minus 0? 5. Okay. Why did we do it? Well, we did it because I want to make sure that this 0 is represented in this list over here. Okay? For the system that we're working in, this doesn't help us because we don't have a 0 in the Babylonian system. But in some of our other systems, we will. So that 0 being represented there in the process by which we're doing this is going to help us in the long run. The last number we always divide by is the ones place. How many ones are there in 5? 5. 5 times 1 is 5. And we will always end up with a 0 when we're done. Now, the answer is these values over here. But they need to be written with Babylonian numerals. So how do I write the number 12 in Babylonian? Not 12 ones, but we'll have some ones.
One, like, side arrows.
Okay.
And one.
Yeah, no, you're good. Okay, so we're going to repeat digits. Absolutely going to repeat digits. And if we don't have the ability to do something bigger, we would have had 12 ones. Thankfully, we do have a tens place, so we're going to write the 10, the arrow, and then the 2 ones. Okay, does that make sense? Okay, this is worth 10. These are each worth 1. The total's 12. That's why those are 12, okay? And then we need to represent 0. And we can't. So we just sort of say, okay, and we move on. That sounds like a very effective thing to do, doesn't it? No, but it's all we can do. There's no other option. Then we're going to have to represent the number 5. How do we represent the number 5? 5 ones.
You could at least, like, separate them and, like, leave a spot blank or something.
Okay, so let's say that we did. We could I kind of did it so that it looks like there's a space here. Let's say that there is a big enough space here that we can at least distinguish the 5 ones from the 10 and the 2 ones, right? We might be able to accomplish that, but even if we did that, we still don't have a way to represent that there's a 0 in between them, right? So we could still say that, yeah, I see the 5 and I see the 12, but maybe this is 12 60s and 5 ones. Yeah? So if you take a look, I think it's on the next page. No, I don't have it written down here. I just have it written in my notes at the bottom. There's a problem on 2 counts with this number. The first count is there's absolutely no way to represent the 0 in between. And the reality is that while I've sort of put in my own spacing there, that doesn't necessarily have to be there either. Can you see that if we wrote this close enough together, it would also look like something else? What would it look like? 17. And if a number that's 43,205 also looks like the number, what is that? 100 and, I don't know, what is 12 times 60 plus 5? Somebody do that for me real quick. Is it 725? I have absolutely no idea.
That's not right.
That sounds like not quite enough.
725.
Is it 725? You did 12 times 60?
Yes.
And then plus 5? Okay. Excellent mental math. Well done, Ty. 725. Okay, so if the number that's really supposed to be 43,205 could also be incorrectly assumed to be 725, or potentially even worse, assumed to be 17, we've got a problem, don't we? Oh yeah, we got lots of problems, in fact. Yes, Savannah?
Okay, so what is that number, like, how would you get that number to 43,205 if it was asking you to, like, revert it back the other way?
You couldn't.
Okay, so if that was given to us, what number should we say?
If you were asked to write down 43,205, you would be still writing it just like this. This is 43,205.
I meant, like, if they give you the symbol.
17, right?
If you were given this symbol as a number, you would be writing 17 probably. Yeah. Yeah. It's a problem, right? It's a problem. Okay.
Did they use the system very, very long?
I mean, the Babylonians are considered to be a very intelligent culture. So, but do you remember the Babylonians were also the ones that told you the world was going to end in 2012? I mean, you guys were alive in 2012, right? You're still alive. You were really little. But did you know that the world was supposed to end in 2012? I mean, that's not the only time it was supposed to end, but it was also supposed to end in 2000. Wasn't alive in 2000, sorry. It was supposed to end before you were born. It was supposed to end. My grandfather was preparing for it. It was a real deal. Oh, yeah. But the world was also supposed to end in 2020 for other reasons, right? The world's been supposed to end a long time, but the Lord tells us that he alone, God, knows the day and the hour. So, here we are. Mayans. I take it back. The Mayans are the ones that did the calendar. My bad. Not the Babylonians. The Babylonians predated the Mayans. So scratch that. It's the Mayans. The Mayans at least have 3 symbols. They have a dot. The dot is worth 1. They have this sort of little bitty horizontal line. It's worth 5. And they have this shape at the bottom here that's a shell. It's supposed to look like a shell. Imagine like a shell, that opens and closes, like it's got the pearls in it. Imagine that kind of shell, okay? A clam shell, yes, thank you. It's actually worth 0. Ooh, we got a 0. It's very exciting. We got our first 0. The Mayans brought us the number 0. But again, their symbols are not worth very much, are they? So there's got to be something going on. And it is something very much like the Babylonians and like we do with our place value system. They have a place value system, okay? They have a modified base 20 system. So do you know why we have a base 10 system?
Because we're 10 digits.
Because we have 10 digits on our little fingers, right? If we were like Fred Flintstone, do you guys know who Fred Flintstone is? Or George Jetson? They have 8. Okay, if God had made us with 4 fingers plus thumb, whatever, they'd be only 4 on each hand, undoubtedly we would have a base 8 system. We have a base 10 system because we have 10 fingers. So why do you think the Mayans had 20?
Did they count their feet?
Yeah, say it louder, Sarah. Toes, right? Yeah, I know. Like, they didn't have closed-toe shoes. In fact, most of you are wearing closed-toe shoes today. In fact, maybe everybody. But in the summer, do you wear sandals? A lot of us do, right?
They counted.
Well, I probably did when they were little. Yes. Yeah, fingers and toes. Modified base 10 system. Okay, well, what is about the modified part? I'll come back to the modified part. It's not exactly base 20, but it's a modified base 20. They also have a vertical system. So instead of writing the numbers from left to right or right to left, right, sort of horizontally, the way that we do, and the way that the Egyptians did and the way the Babylonians did, they write them top to bottom. They're not the only culture that does this. We do not talk in this class about the Chinese culture, but traditional Chinese numerals are written top to bottom as well. They're written vertically. So this is not the only culture that does this. The Mayans are the ones we're going to talk about. They do this. And what they do is they put the bars under the dots, or they put the dots above the bars. Okay, so if they want to represent the number 6, it'd be a dot and then a line. Okay, let me write that one down so that you have that one written too. So the number 6 in their system would be a dot over a bar. That's 6. If you saw a bar over a dot, your place value would have to change right there. Let's use a darker color. Right there. Because dots don't go under bars unless it's a different place value. Okay, so are you with me? Like with the Babylonians, smaller numerals in front of bigger ones force there to be a change in place value. Same thing here. If you have bars over dots, it forces a change in place value. Okay, so then let's talk about this modified base 20 business. So in the Babylonians, we had bases of 60, right? We had a base of 60. We had the 1s place, the 60s place, the 60 squared, 60 cubed. If the Babylonian or the Mayans were a base 20 system, it would look like that. You'd have the 0s or the 1s place, you'd have the 20s place, the 20 squared, the 20 cubed. Everybody good so far? Okay, powers of 20. I'm going to write their powers of 20 from the bottom up because they write it vertically. So the 1s place is on the bottom, and the 20s place is above that. That's all good so far. If it were a base 20 system, the next thing I would write is 20 squared, yes? Okay, they don't do that. They do 20 times 18. Okay, let me continue showing what they do, and then we'll talk real quickly about why it's happening. After that, they do the powers of 20. So now we've got 20 squared times 18 and 20 cubed times 18 and so on. Now, each of these have values. Like there's actual, I didn't mean to do that. Let me move that over. Each of these have actual values. Let's figure out real quick what they are, because it will answer partly at least the question of why they did this. Obviously, 1 is 1 and 20 is 20. What is 20 times 18?
360.
360. Let's write down a couple more just so we have them written down for later. What is 20 squared times 18?
7,200.
And what is 20 cubed times 18? Do you have that one, RJ?
Okay, 144,000.
You got it. 144,000. Thank you so much for getting those for us. Okay, so the one that's sort of showing up here where the first 18 gets introduced, 360. Why do you think 360 was an important value to them?
That's how many days were they?
Days. Who said it? Days. Kiki said days? Yeah, you're right. It's days. The Mayans were famous for calendaring. That's why their calendar is the one I was talking about inadvertently before, stopping at the year 2012. Okay? Very infamous for calendaring. And there's about, right, think ancient culture stuff, about 360 days in a year, right? That's why they wanted that number 360 to be part of their place value system. Okay, so that's what's going on there. All right, we need to stop right there. We will come back next time and we will talk about looking at numbers before, after, and converting with Mayans. And we will see that they also have a problem even though they have a 0.